In this screencast, we will look at how we can work efficiently with deep learning models on the Axis cameras. We will see how we can do rapid prototyping and how we can efficiently debug when our model doesn't work. We will do this by seeing how we can mount our local development code directly in the camera so that we can directly run the code without having to transfer it over to the camera each time we make a change. We will see how we can run IPython interactively on the camera and using a browser stream to stream images as we show them interactively in the IPython terminal. And we will see how we can work with the Docker containers and images in an efficient way. And we will also look at how we find the debug data from Larod, the deep learning inference daemon in the Axis cameras. So this is the second video in the series. In the first screencast, we went through a step-by-step instruction for how we can build and run the deep learning models on the camera and then Axis 𝗵𝗵𝗿 camera. So if you don't know that and haven't watched that video yet, go and look at that one first. But for now, let's get started. So the first thing we're going to look at is how we can get our local development code mounted directly in the camera so that we can run it from there. So the way we're going to do this is that we're using Samba NFS storage and running a Samba server on our developer computer, which we can then mount from the camera. And this is very straightforward. We can find instructions on the Ubuntu website for how to install the Samba server. And then we just set up a Samba share and point it out to our source code. And I like to put it as read only so that I can't do any changes from the camera. The next step is that we need to go to the camera's web interface, and we go to System and Storage. And here we can attach the network storage. And we can see that I have already attached the shared source folder on my development computer. And we can verify this by doing an ls in this development folder. And then we can SSH to the camera. We can see that we have actually mounted network share. And if we cd to that location, we can find the same files as we had on our development computer. So now that we know that this is working, we want to use this to run the application with a deep learning network. So first thing, we need to start the TensorFlow inference server, the TFServing server. And typically what we do there is from the Axis examples, we can see that we have the models put into the Docker container or to the Docker image that we need to transfer to the camera. But I find this to be a very slow way while you're developing the code. So since we already have mounted the code in the camera, we can mount the model too. So what I typically do is that we download the model locally. So in the examples, this is done in the Docker file.model. So instead, we download this network to our development computer. I'm gonna rename it to model.tflight. That way I can easily switch between different models. And next thing is that we need to tell the TensorFlow serving server to not look for the model that is in the Docker container, but rather mount it from the camera, which has mounted it from our development computer. So first off, I have created an environment file which I can source, which sets a few different parameters. So for example, the camera IP and the name of the application and some other things that are needed when we build the Docker containers. But it also sets the debug model path to the model that we just downloaded. And this path is set to a path which we will mount it onto in the Docker image or the Docker container. So the next thing we do is that we have our Docker compose.yaml file. I have made a new one which I use for debug purposes. So this one is called Docker compose debug.yaml. And if we look at the difference on these two, we can see that here are a few differences. So for example, I've changed the path to the image, and that is something we're going to talk about later, to use ECR on AWS instead of pushing the image through a pipe to the camera. But the main difference is that I have removed this Docker image where we found the models before, and instead I mount the network share into the Docker container. And I do this for the inference server so that it will find a model. And here I have made a few changes in how we start the inference server. So we point it to the debug model path, which points to the model in our mounted NFS share. That is the main difference here. But I also made a few changes so we actually export environment variables. And this is because if we run this container interactively, it's much easier to debug why it doesn't work when there is issues. Next, we also mount the network share into the application image. We will run our Python application. And here I set the working directory to the path that we have our code in. And I update the entry point to bash so that I get an interactive terminal per default. So with these changes, we can start by starting the inference server. And typically we would just do Docker compose up, but in this case, I just want to start the inference server. I don't want to start application. So I specify inference server here. And the usage of this command, docker compose cam, that was also something that we could see in my end file. So here I set two different aliases. It's one for docker compose cam, which runs the Docker compose and points it to the axis camera. And the same for Docker. So that means that if I run Docker PS, for example, I have the Docker images. So here we can see the images that I have on my local computer. But if I do Docker cam images, and I see the images that are actually on the camera. So I use the same client for my development computer pointed at either the Docker daemon locally or the Docker daemon in the camera. Okay, but we can see that we started the inference server on the camera. So that is running, which means that we can start our application. And what we're going to do here is that we run the pose estimator, as the service is called, in the Docker Compose file. So instead of doing Docker Compose up, we do Docker Compose run, and this gives us an interactive terminal in the Docker that is running on the camera. So we can see that since we updated the work directory, we get directly to our code. And here I can see into the app directory, and we have the detector with 𝗏𝗏𝗏, which is our main application. So let's execute that with Python. We should have a 𝗏𝗏𝗏 server starting up on the camera. So going back to the camera website, our web server on the camera, we can go to port 5000 instead, and we get to our application. Here we have the application running on the camera. So since we now have mounted the code, we can easily, if we want to make any changes to the code, this is the code on my local computer, which is mounted into the camera. So let's, for example, say that when drawing the key points for the detections, I also want to draw the confidence score. We're going to put text on the image. The text should be conf, one decimal place, and let's actually multiply by 100, so we get it in a percentage of the maximum confidence. And we're going to put it in the same place as the as we draw the detection. Use this font, scale factor, let's set that one to 1, and the color can be red. Okay, so now we should hopefully draw the confidence on the image too. Let's see if it works. It does something, but the text is a bit too big. So let's edit it again, and we can set the scale factor to 0.4 instead. Okay, so that is a bit better. So already now we can see that it is much faster than if we were going to build a new Docker image with the code and push it to the camera and restart the whole image. But we can actually get even nicer than this. So one of the changes I did to the Docker image that we are building and pushing to the camera is that I installed IPython. So that means that on the camera we can run IPython. And this is really nice. So what we can do here is that we can import CV2, and we can do capture, and then we want RGB values, so we need to set the, let's actually paste this from the code. What we do here is to set the capture to get us RGB images. I think the standard is NV12 or possibly grayscale. So now we can do frame equals to cap.read. We should have a frame, 1080, 1920 times 3. So that sounds like a frame. Now we want to look at the frame. So what I have done is that I have modified the web server so we can actually use that one interactively too. So let's do from, let's see, the file is called detector with Flask. Import the detector to actually run the POSE estimation net. We're going to import a show method and a start server method. So with these methods, I can do start server, which will start the Flask server. If we refresh this now, we should have an active stream going. And let's do like this so we can see the browser too. So let's start by showing our frame and see what that looks like. So that is the frame we captured. If we want to do run this through the network, we should make it a little bit smaller. So I'm going to do small frame equals, first I'm actually going to initiate the detector instance from the detector class. Small frame equals detector.preprocess. This will give us a small frame, or an image which is the correct size for the network that we are running. So next we're going to do the inference. It's detect. Perfect. So we can see that we now have a few different points. And we can see the different confidence scores for these points. So if we now want to visualize these, we can do frame equals detector.draw key points, and we're going to draw it on the small frame, and we have key points and confidence. There we can show the predictions on that frame. So this gives us a nice ability to interactively debug and try different things that we want to develop. And of course, as we create the code, we can add it to the code files and integrate it step by step. So let's go back to the terminal here. And we're going to have a look at what we do when things doesn't work, especially when our network doesn't do, or rather when the network doesn't want to run at all. So there are a few different ways that we can get information about the inference. But the first thing we're going to do is that we go into SSH to the camera, and let's actually start with, we close down the TensorFlow serving server. Stop the model server. And here we're gonna SSH to the camera, and we're going to tail the system log. The system log is always good to have an eye on what is happening there. But we can also get messages more specific to the inference, and that is by doing a journal CTL and look at the logs for the Larod, the inference daemon. So here we can right away see that when running the network, we had a bunch of issues. And these kind of issues typically indicate that something in the network is not compatible with the hardware, which means that at least some of the nodes will probably run on the CPU instead of on the DLPU in the camera, making it significantly slower. So one of the common things I see here on 𝗏𝗏𝗃 is that a lot of the networks are quantized per axis or per channel quantized, and that is not supported in the 𝗏𝗏𝗃 DLPU hardware. So there it needs to be instead tensor per tensor quantization. And that should typically be done when training the network. And if this is not done, the network will take very much longer time than if you actually do it correct. So keeping an eye on this log will give you a good indication on if there is headroom for running it faster on the camera, or if you need to look at other optimizations. So now when we have the two logs open, let's start the inference server again. But instead of starting it with the attach as we did before, we can start it and keep attached to it. That was the wrong service. So this will do exactly the same thing as we did before, but we will have the logs open. So if we run the application again, then if there is any issues with the inference server, we'll see the logs from the image. But what if there is an issue with the inference server, for example, that doesn't find our model? So let's move our model, just rename it to something else, and I try to start the server again. And now I see that I get an error message saying that I have failed to open file, no such file or directory. One way I can do to to debug this is that I can also here do a run instead. And we can override the entry point bin shell. And here we had exported variables, so we can cd to model path. And we can do an ls here and see that it's mounted the code folder correctly, at least. But we can see that the issue is that the model doesn't exist with that name. And so we can try to rename it again to model.𝗃𝗏𝗁 and do it from here because we want to read only. But we can close this one and rename model.𝗃𝗏𝗁. And we can see that it's renamed here too. So now we can try to run the inference command with the standard options from the Docker file, and we can point it directly to model.𝗃𝗏𝗁. So now it seems to work without complaining. So then we can try to run our application again. And hopefully we should get some predictions. Yep, we got 2 predictions there. So this seems to work fine. So just by doing these tricks to actually find what is going on in the different services, we can get quite much information. If we want to go even more granular, in some cases it might be worth to actually go straight for the Larod inference API instead of using the TensorFlow serving. But typically I find TensorFlow serving very nice for both debugging and for actual live inference. So another thing that we could have issues with is what if our Flask server doesn't work as it is supposed to do if we can't access the port. So if we can't access this URL when we have the application up and running, how can we then debug it? So for example, we can start the application again. We see that it's now running the server on port 5000. So let's go back here. And what we can do now is that we can do docker cam ps and still in the Docker container. We can do docker cam ps and see what images are running. And we can see that the image is running and it has forward port 5000. And it's listening to all the IP addresses, so it should be externally reachable too. If it was not, we could do docker cam exec, and we can take the ID of this container and let's set entry point to bin bash, and we want to do it interactive. So now we're we have entry point set. function container command. Interactive. Okay, so that's how we do it. So now this terminal is actually inside this running Docker container. So we can start with using curl to the loopback address and see. So this is not installed in the Docker image, but we can easily install it as long as the camera is connected to internet. Let's install curl. Okay, so let's again try the curl in the URL. And yes, we see that it is working. So next, if this is actually working, we can actually look at netstat too. I don't know if this is installed in the container. Something to be, but we could install that here too, just as we did with curl, and see that the port is actually listened to by a process. But now, since we confirmed that it does work within the container, we can see is the container running correctly. For example, if I didn't have this one, we wouldn't expose the port outside of the container. So in that case, we would see that it works inside container. But if I instead SSH to the camera where the container is actually running, we can do curl here too. We see that it is working here too. And here we have netstat. We can see here that something is listening to port 5000. So now we have confirmed that it is actually working locally on the loopback address of the camera. So if it is working here but not on our developer computer, then it's probably a network issue, or we are listening to our loopback address but not to external connections, as we can see here that we are doing. But in this case, I can of course do curl to the camera address and see that it does work here too. And naturally it does work in my browser also. Now we can, however, see here that we get an error message, failed to connect to the gRPC bus, because we are not running our inference server. And we can see that if we do PS and the camera Docker. So again, then we have to start our inference server. And we can run the post estimation app again. So this is a typical workflow that I am using when debugging why it is not working. So you want to break it down and take it step by step. Start as close as possible with as few different programs and processes and networks and so forth in between as possible. And then you gradually expand until you find where the issue is. So that was a bit about debugging. And let's now talk about actually building Docker containers and pushing them. Because even though using this method, we don't need to push a lot of Docker containers, since we have the code mounted in the camera and in the container. We can just change the code and run the code on the camera directly. But in some cases, we need to rebuild Docker containers and push them to the camera. Perhaps we want to install new libraries or something in the container that we need for our runtime. And one way of doing this is that we can do Docker save. So this is what you find in the Axis examples. So we build application and we do Docker save. We pipe the output of this to the Docker camera and loads it there. And this can be very inefficient, since it basically compresses the whole Docker image and pushes it to the camera in one stream. While the normal Docker push and Docker pull commands, they are working with caches of different layers. So if you just do a tiny change in the Docker image, you don't need to actually push the full image. And we can do Docker images Docker images. So you can see here the latest image I pushed to the camera. It's 600 megabytes. So it's quite large images, and piping them this way takes a long time. So we really want to make use of the caching layers in Docker. And we can do that by using a Docker registry. And Docker Hub is, of course, one registry. But if we do internal projects, then we don't want to push our Docker containers to Docker Hub. So instead, we can use, for example, AWS, Elastic Container Registry. So you do, of course, need an account on AWS. But when you have that, you just go to ECR and you create a new repository. And that's basically as easy as giving it a name. And then you will get an URI to your repository. And you make sure that you tag your images with this. So in my case, I have the N file. And here I have exported the Docker URL, which is the path to my AWS ECR account. And when we looked in the Docker Compose file, we could see that I have replaced the image with this Docker URL and the application name and latest. And that means when I do some changes in the Docker file, so let's, for example, I might want to install TQDM in our Docker image too. Now I want to build the Docker image, and I want to tag it with this name. We can see that the first 18 layers were taken from the cache. So it's just a few layers that are updated now. And actually, if I would instead do this, then we can reuse the last layer too. And we see that also layer 19 was taken from the cache. So we're just rebuilding the last 3 layers, which should be quite small. If I want to push my container, and before I can do this, if I just set up easier, then I need to do a login. So I get the one-time password through the AWS CLI, and I configure my Docker client with this. And this will actually configure the client both when using our local Docker daemon on the developer computer, but also when using the Docker daemon on the camera, since we are using the same client and just instructing the client to talk to another daemon. If we have run that, then we can do push our image. Should be quite fast since we didn't do many changes. And then we can pull the image to the camera. So we can see that that was really fast. If we do now run the we run the application once again. Python. We can see that we have pqdm installed. And if we just wanted to do this for debugging purposes, then we could, of course, install it directly in the camera without rebuilding and pushing and pulling the Docker images. But that way it wouldn't be persistent, of course. When we stop the container, it disappears. So this was a really fast way to change the Docker container, build it, push it, pull it, and run it. If we compare to the save and load command. So now I have already pushed my latest container to the camera. So we actually have all the layers cached on camera. So there is no need to transfer any information at all. But if we run this now, we will see that it takes quite some time, because the client that is saving the Docker container and piping it through the pipe to the other Docker client on the camera, that one is not, it doesn't know about which layers are cached on camera. So it just sends everything from start, even though all the 23 layers was already there. All the information was in the camera. So that is why you should definitely make use of a container registry like AWS CCR. Yeah, so still running. And with that, we end this video. So we have now gone through a lot of things: how we can mount the code, how we can run IPython on the camera, how we can work rapidly with the prototyping, both using our different Python scripts that we can change directly on our developer computer and run them directly in the camera, but also working with the interactive terminals in the camera. And we have seen how we can work with the containers, both pushing and pulling them quickly to the camera, but also how we can find debug information, run it in interactive modes, and enter the different containers and see what is actually running in each container. So in the next video in this series, we will take a look at how we can build a full pipeline where we can train a model, we can quantize the model, and we can convert the model to the format that it needs to be to run on the camera. And we're going to do all of this in a pipeline in the cloud, and then seamlessly push it to the camera and update our application. So that will be an interesting video.